For those of you who just want me to cut to the chase, I'll start this video with a quick summary of the temperature profile for an instrumented uncovered basin in response to a 2-inch storm. I'll then dive a little deeper into temperature and humidity data recorded by an AM2315 and SHT10 sensor before and after that 2-inch storm. I'll also share some discrete measurements I collected before and after that storm and summarize some preliminary conclusions from the collected data. I'll end by sharing details regarding mulch selection and application in advance of the next storm. This information can help us estimate baseline conditions in order to qualitatively understand how mulch can impact temperature and moisture profiles, keeping in mind that this experiment is taking place in a natural open setting. So here's a summary of my setup. This is a basin I cleared in my backyard for logging air temperature, shallow soil temperature about 1 inch beneath the basin surface, and deeper soil temperature about 6 inches beneath my setup. All this data will be logged to an Adafruit IO dashboard using a Feather Huzzah ESP8266 for ease of data review from inside my home in real time. All my sensors also log relative humidity, but as I'll explain shortly in the video, I've learned humidity is not a very sensitive parameter for understanding the soil moisture profile. Here's a snapshot of the temperature profile for those 3 sensors in late July. Here you can see when we witnessed our first monsoon and the impact that had on relative temperature between all 3 sensors. Note that before the storm, shallow soil temperature captured by the green line is significantly higher than air temperature, but after the storm, the trend is reversed, with shallow soil being relatively cooler than air temperature. After the storm, you can see here that there are 2 peaks where air temperature is higher than soil temperature. And this is the first day when shallow soil temperature rises to the same level as air temperature. And finally, here's the first day when shallow air temperature briefly exceeds air temperature. With this data in hand, I can come up with an estimate of how long it takes the shallow soil profile to dry out using temperature as an analog for moisture, where it takes about 80 hours for the cooling effects of soil moisture evaporation to start to become muted in the shallow 1-inch layer of soil in this basin. And this shows the general trend over time after that storm event, suggesting that cooling from deeper evaporation is being buffered as additional moisture from the basin is lost in the absence of rain. So here's the temperature profile for my 3 sensors before our first significant monsoon storm. Here you can see that the shallow temperature recorded by my sensor just beneath the soil surface is significantly higher than air temperature, and that things are pretty constant over time. I have an idea as to why this is happening, and to explain it, here's a conceptual model of our setup showing where temperature is being logged. I'm only going to focus on the shallow soil and air temperature sensors for this summary. During daylight hours, the sun introduces shortwave radiation to the site. This causes the soil to heat significantly and also emit long-wave radiation that is heating the air as is being registered by the AM2315. I suspect that since the air sensor is relatively close to the ground, I'm probably getting a little bit of bias in my air temperature readings. But regardless, what we can see in the data is that the conversion of shortwave radiation to long-wave is having a greater impact on soil temperature relative to air temperature. You might have experienced this firsthand when you walk on a beach on a sunny day and the sand burns your feet even though the air temperature might be relatively pleasant. Next, we can see the impact that our monsoon has on our temperature profiles. Shortly thereafter, we see that the trend is flipped, with air temperature being higher than shallow soil temperature. In this case, let's return to the conceptual model. When a storm hits, we get some infiltration of moisture at our experimental site. This rain immediately cools both the air and soil temperature profiles, as we can see in the data. When the sun comes back out, that moisture starts to evaporate. That evaporation becomes the new bucket for all that incident energy from the sun, resulting in the soil profile being cooler relative to air temperature. As evaporation continues, The soil profile continues to dry, and evaporation starts to play a smaller role in cooling our basin. We can witness that over time as soil temperature slowly rises over the course of the following days in the absence of rain. To establish a baseline, we can determine how long it takes for the shallow soil and air temperature profile to equilibrate, which in the case of my experiment is about 80 hours. After that equilibration, we can see that the trend starts to reverse back to what we witnessed before the storm, with soil starting to become warmer than air temperature for brief periods each day. In addition to soil temperature, the SHT10 can also monitor soil humidity. Here, you can witness a strong signal in response to the monsoon. Note that the shallow humidity now approaches what my deeper SHT10 is measuring at a depth of 6 inches. However, if you look at the soil profile after the storm, you'll notice that there's significantly more moisture in the shallow area relative to the deep, and yet both sensors are reporting the same relative humidity. So what's going on here? I reached out to a colleague at the Walnut Gulch Experimental Watershed run by the Agricultural Research Service who showed me this graph which demonstrates that soil humidity is relatively insensitive to soil moisture in dry or wet soils, confirming that the SHT10 is not a good indicator of soil moisture. Instead, I'd be better off working with one of these soil capacitance sensors, which will report back an analog response in proportion to soil moisture. Since the huzzah I'm using to talk to the Adafruit IO platform only has one analog pin, which I'm using for monitoring battery voltage, I'll have to use this Adafruit Stemma soil moisture sensor, which works over I2C. This is something that's pending for a future chapter in this series. Next, I'll summarize some periodic field observations, including temperature checks collected before and after the monsoon. So I've been checking in on this installation over the course of the day between tasks, and I noticed that my shallow temperature shot up to 141 degrees. That's for the SHT10 that's just buried about an inch beneath the soil surface. That seems really high, so I'm going to compare that to what's going on outside. So now I'm outdoors, and let's see what this soil measures with this little Suntech thermometer. So that's telling me that the surface is 156.2 degrees Fahrenheit on this bare soil, which is why I probably can't grow anything back here. I mean, that's hot. I'm going to go ahead and take a measurement of the PVC. And that's coming back at 121 degrees. I am going to get another thermometer though, maybe a glass thermometer that I can use to better understand what the air temperature is for comparison. I'll take it. And here's a few measurements collected with the bulb thermometer for comparison with the AM2315 collected before the July 23rd storm. The soil humidity is still relatively high, even 48 hours after the significant rainfall we've had. So it's also interesting to note that the soil temperature now is much lower than what the air temperature is, probably because of all the evaporation that's taking place out of that soil profile that's absorbing energy and causing the temperature to fall, very similar to when we sweat. Okay, my AM2315 is reporting about 98 degrees Fahrenheit, so let's see what the thermometers say. About a 99, and let's get these straight. Looks like I got about a little over 99 and 100 degrees, so between 1 and 2 degrees of accuracy, depending on which one of these thermometers you want to believe. All right, folks, it's July 29th. It's about 12:30 in the afternoon. I think the temperature is probably about 110 to 112 degrees between the soil and the air temperature measured by the AM2315. And I found something really interesting. When I picked up this brick, I noticed that the soil was still wet underneath. Wow, pretty wet too. I mean, it's been like 5 days and there's still a lot of moisture here where the soil was covered. But if you look at the area that isn't covered, I can do the same experiment and the soil's completely dry. And that's at the bottom of the basin where the sensors are located. So putting a little bit of cover on the soil can really make a difference with respect to soil moisture. So there you go. Maybe my neighbor heard me and decided to stop blowing all that mulch off his front yard. Anyway, pretty interesting. All right, folks, so it's another beautiful hot day in Tucson. 113 degrees is the air temperature, and the shallow temperature is showing up as 118. So this first thermometer is in the general vicinity of the shallow sensor. So let's see what it reads. And that's at about 119. So that makes sense. Then I put a second thermometer under this brick just to see what it's registering, because things are still kind of moist down under that brick. Now let's get this out quickly. So that's coming back at about 106 degrees. So that's a significant difference between the covered and the bare soil. And while we're at it, I'll just show you what the conditions look like under this brick a week after the fact, after that torrential rainstorm. So you can see here that we still have moisture down here. I can actually feel it's kind of humid right here. So that's the evaporation that's coming off, that's cooling the soil, giving me slightly lower temperatures than what I might find in this bare soil area, which is where my sensors bear. So what are some of the things I can derive from the temperature data collected by my setup? First, it's interesting to note that temperature in Tucson, Arizona peaks daily between 2 and 4 p.m. when things are ramping up for the monsoon. In addition, for the sandy loam soil type in my basin, an intense 2-inch morning storm yielded about a 4-inch wetted profile in soil that was originally bone dry. Next, using temperature as an analog for soil moisture, I discovered that a 2-inch early morning storm took close to 80 hours to, quote, dry out in my uncovered basin. And I should clarify that for the purposes of this experiment, the time for drying out really means the time it took for soil temperature to first reach or exceed air temperature after an intense storm. Next, based on the data collected by these sensors after my storm, I discovered that the soil-air temperature dynamics start to flip closer to what's witnessed in dry conditions, usually around 1 in the afternoon when the sun is high in the sky. Also, the reason I'm using temperature rather than humidity to approximate soil moisture is that humidity is relatively insensitive to soil moisture between wet and dry profiles. In response, I'll soon investigate using capacitive soil moisture sensors to better understand the soil cooling dynamics being driven by evaporation. Also, it's interesting to note that soil responds very similar to a living organism that cools itself by sweating through evaporation. As the soil moisture runs out, the soil temperature slowly rises, similar to heat stroke affecting a dehydrated person. Given this context, it seems that mulch can help us keep our dehydrated patient, or in my case soil, alive through recycling of our green clippings. Specifically, qualitative observations suggest that cover generated by mulch can slow down evaporation significantly over time. And since our storms in Tucson are now much more intense and farther in between, mulch can help us build climate change resiliency by helping us better store the precipitation associated with those infrequent, intense events for longer periods of time, which is something I'll try to better approximate moving forward. You may also notice that I removed this metal mesh, which I originally intended on putting above this basin to help keep those leaves in place. I removed it because I don't think leaves are going to be the best example of mulch that I might find here in the area where I live. So instead, I'm going to be using mulch that was created by chipping wood that I had in my backyard. I think that'll be a little bit denser. It won't be subject to being blown away. Makes more sense as well for the kind of mulch that I might run into where I live. So this thing works pretty good for nothing bigger than an inch, and your twigs better be straight too, but it does make really nice mulch, which would be perfect for the experiment I want to run. So same stuff that I'd buy at Home Depot, only I don't have to drive to the store, and I can just use what's in my backyard. In fact, I'm already spreading it around some of my potted plants here in the backyard to help cut down on evaporation from the same. You can see it right there. That should result in me not having to water these plants as much as I normally do, given that they're in pots. Okay, folks, so I've got my baseline set up. I'm going to go ahead and spread the mulch that I just generated. Today, August 3rd, it's about 8:30 in the morning, and let's see how this impacts my results moving forward. And there you have it. I spread probably somewhere between maybe a ½ inch to an inch of mulch over the sensor area and dispersed it around the basin in general. Looks like my tortoise is coming out to pay me a visit. He's kind of curious as to what I'm doing. But there you go, folks. Let's see if this makes a difference. I didn't want to add too much mulch to begin with. We can add more later if this doesn't seem to have much of an impact, but I figured we'd start small. Hey, Tidbit.